In this video, we're asked to write a method called removeAll that'll remove from a sorted list of integers all values appearing in the second sorted list of integers. So for example, we have the list 1 here and then list 2. So we see that 1, 3, and 5 occur in list 2 and they're already in list 1. So we're going to remove those values when we call list1.removeAll of list 2. And that should leave us with 7 here. And if we happen to call list2.removeAll from list 1, we see that we iterate through list 1 here, and we see that it has a 1, a 3, and a 5 in common with list 2. So we remove the 1 from list 2, the 3, and the 5 from list 2, and we're left with 2 and 4. We are guaranteed that both lists are going to be in sorted order, although there may be duplicates in either list. And we can solve this problem fairly efficiently. So the common thing with nodes is we have access to the front, the data points, and the .next field. Let's get started here. Okay, so our return type is void because we're modifying the linked int list. So public void remove all. It's going to take in another list. So linked int list other. And what are we going to do? I'm going to use a little bit of recursion here, using the x equals change x theorem. So I'm going to change the front to be equivalent to remove all helper, and what I'm going to pass into this is I'm going to pass in two linked int lists so that I can compare the two and then start removing things from there. It's going to take the front and then it's going to take the other dot front. Alright, so our private method should return a list node and remove all, and it's going to take a linked int list. That's going to be equivalent to f1. Then it's going to take a second linked int list, we're going to call it f2. Okay, so let's start with the base cases. What if f1 is null or f2 is null? Then at that point we don't have any comparison, so we can just return f1 at that point because we're not going to change anything. So let's deal with that case first. So if f1 is equivalent to null, or f2 is equivalent to null, then we'll just return f1. Okay, now let's deal with this other case here. What do we do if front 1's case, or front 1's data is less than front 2's data? Then, so for example, we move on to, well, this doesn't show it very well, but say we're looking at list 2 and we want to compare to list 1. We compare these two values. Okay, let's progress even further. So we reach this point where it's less than. So what do we want to do? We want to move this cursor forward while keeping this one in the same spot. So, else if f1's data is less than f2's data, we keep the cursor for f2, but we change the front for front 1. So we're going to say f1 dot next is going to be equivalent to remove all helper. We're going to say f1 dot next so we can progress forward, and f2 is going to remain the same. Now, what happens if we deal with the opposite case here, where f1's data is greater than f2's data? Then in this case, we want to do the opposite, and we want to say, okay, let's say f1 is going to just stay the same, and we're going to just progress f2. So remove all helper f1, and then we'll call upon f2.next. And then after all of this, we know that f1 and f2 are equivalent to one another. So we're going to actually skip one of the nodes here. Like for example, we're pointing here and we're pointing here. We want to skip this value, so our f1.next will be pointing at f1.next.next. And the way we're going to do that with recursion is we're going to say, okay, f1 is now equal to remove all helper, and it's going to take f1.next. And then f2 is just going to be the same because we might have duplicates that we need to look at. And then at the very end, we just need to return f1. And that's it for this video.